Go for Excel.
The last time anyone, besides a fighter pilot, flew faster than the speed of sound, it wasn't in some cutting-edge new aircraft. It was in a machine that first took off over 50 years ago. A jet that didn't just break the sound barrier, it cruised beyond it. That jet was Concorde, and today the only way to experience one is behind a velvet rope in a museum. And yet, scroll through the internet for just a few seconds, and it's clear there's a hunger for speed. Supersonic travel still captures the imagination. It's sleek, it's powerful, it's futuristic. So why, with all the modern technology, private investment, and global connectivity, does every attempt to revive it seem to crash and burn? It's not because people don't want it. It's not even because the tech is impossible. It's something much bigger and more complicated. So let's dive into it. Why does every new supersonic jet fail? And is there really no way to bring back that golden era of fast, luxurious flight? To understand why supersonic jets keep failing, it helps to look at the one aircraft that actually worked. The Concorde didn't just go fast, it rewrote the idea of what air travel could be. New York to London in under 3 hours, every seat first class, champagne, caviar, duck l'orange. This wasn't just speed, it was luxury at 60,000 feet. But for all the glamour, a step inside the Concorde today reveals something surprising. The cabin is cramped, the ceiling's low, especially near the doors. Windows? They're barely the size of a paperback novel. But every one of those design decisions served a purpose. Smaller windows slowed cabin depressurization, narrow bodies reduced drag. Every inch, every curve was built for speed. And pilots? They weren't just flying the plane, they were rubbing shoulders with rock stars. Seriously, pilots have stories of the Rolling Stones and Beatles asking for cockpit tours mid-flight. It wasn't just a jet, it was a scene. But then, almost overnight, that scene ended. The beginning of the end came in July 2000. A tragic crash near Paris exposed a critical design flaw. A piece of metal on the runway punctured a tire, which threw debris into the fuel tank. Fire erupted, the plane went down, everyone on board was lost. It was more than just an accident. It was a turning point for the entire industry. The investigation revealed how even a small oversight on the ground could bring down one of the most advanced aircraft ever built. Confidence in supersonic travel was shaken overnight. Ticket sales dropped dramatically, and airlines began questioning whether the prestige of flying Concorde was worth the risk. Regulators tightened safety requirements, and insurance costs skyrocketed. Public perception shifted too. The jet that once symbolized progress and sophistication was now seen as dangerous and outdated. Even though engineers quickly made design changes to prevent similar incidents, the damage to Concorde's reputation had already been done. And when safety fears collide with rising operational costs, airlines tend to walk away. That crash wasn't just the end of one flight. It was the moment the dream of routine supersonic travel started to slip through aviation's fingers. Though Concorde flew again briefly, its fate was sealed. It wasn't just the crash, it was the cost, the noise, the fuel, the regulations. All the things Concorde barely got away with for decades were suddenly under a microscope. On November 26, 2003, Concorde landed for the last time. And since then, no passenger has traveled faster than sound. But that hasn't stopped companies from trying. In fact, right now, there's more activity around supersonic travel than at any time since Concorde was grounded. Boom, NASA, Lockheed Martin, Venus Aerospace, Hermeus, all chasing the dream of flying faster than sound. But if Concorde actually worked, why hasn't anyone been able to recreate it? The answer starts with something that's hard to see, but impossible to ignore: the sound. Sonic booms are loud, like really loud. Think chainsaws, car horns, or glass shattering overhead. Not once, not at takeoff, but constantly, for as long as the plane is flying supersonic. And that's why, in 1973, the US banned supersonic commercial flight over land. Most countries followed. So the Concorde, it only went full speed over water, no sonic boom over cities. That regulation still exists today, and that's a problem, because 78% of the demand for supersonic flights is actually over land. If jets can't fly fast over land, the market shrinks dramatically. Boom knows this. Their new Overture jet won't even try to reduce the boom. It'll just fly over the ocean where nobody can hear it. But that's not innovation. That's just working around the rules. The X-59, though? That's trying to change the rules themselves. This isn't a commercial jet. It's a NASA experiment designed to retrain the ear. The idea is to replace the sharp boom with a gentle thump, something closer to a car door slamming than a cannon going off. To do it, they've reshaped the plane entirely. The engine is mounted on top. The nose is a ridiculous 38 feet long, and every inch of the body is designed to manage how air compresses, keeping shockwaves small and spaced out. But that's not the only trick. Flying higher can also reduce the impact of a sonic boom. At 100,000 feet, the boom becomes virtually inaudible to human ears. But flying that high comes with a new set of challenges, ones that feel more like space travel than air travel. At that altitude, the air is so thin that if cabin pressure fails, your blood doesn't just lose oxygen, it boils. It's called the death zone for a reason. Military jets like the SR-71 Blackbird had to suit their pilots up like astronauts. Pressurized suits, specialized oxygen systems, because any mistake at Mach 3 at 85,000 feet could be fatal. And these modern concepts, they want to go even faster. Hermeus Halcyon aims for Mach 5. Venus Aerospace wants to hit Mach 9, 9 times the speed of sound. But here's the thing, the faster you go, the more heat becomes a problem. At supersonic and hypersonic speeds, heat doesn't just rise linearly, it explodes exponentially. The SR-71 hit skin temperatures of 600 degrees Fahrenheit. The glass in its cockpit was thick quartz. The tires had aluminum to resist heat. Even the fuel tanks expanded during flight. Now imagine doing that at Mach 5 or 9. Aluminum melts, composites break down. You need exotic materials, titanium, reinforced carbon, maybe even ceramic tiles like those used on space shuttles. And that's very expensive. Hermeus is trying to solve this with a hybrid engine, using a ramjet wrapped around a modified F-16 jet engine. It's a clever idea, but even they admit that testing is difficult. There are only a few facilities in the country capable of handling the speeds and temperatures involved. Most are booked out for years. That's why they opened a new test site in Jacksonville, Florida, to speed up their roadmap and reduce reliance on bottlenecked government infrastructure. But building the engine is just one part of the challenge. Getting regulatory approval, finding test space, that's a whole different beast. Right now, there's literally one place in the entire US where a plane can legally break the sound barrier over land. Edwards Air Force Base in California. That's it. It's a massive, flat patch of desert flanked by dry lake beds used by NASA and the military for some of the most cutting-edge flight tests in history. This is where Chuck Yeager first broke the sound barrier in 1947. It's where the X-15 screamed past Mach 6, and today it's the only real playground for modern supersonic prototypes. But even here, space is limited. Every test has to be scheduled around military operations, safety zones, and environmental windows. The weather matters, the altitude matters. Even the time of day can impact how a sonic boom travels through the atmosphere. And here's the kicker. It's not just test flights that need this airspace. The same narrow corridor is used for engine trials, acoustic testing, and sometimes unrelated military exercises. So companies working on supersonic aircraft often find themselves in a long line, waiting for their shot to prove an engine or airframe works. That kind of bottleneck slows everything down. It's not just about building the plane anymore, it's about finding the room to prove it can fly. And even then, engineers have to wait for very specific weather conditions, or else risk collecting useless data. And then there's the elephant in the room. Fuel. The Concorde burned over 22 tons of jet fuel per hour. Compare that to a Boeing 737, just 3 tons. The math is brutal. Per passenger, Concorde's emissions were roughly equivalent to everyone on board driving from London to New York in a Ferrari. Modern companies know this. That's why they're betting on sustainable aviation fuel, or SAF. It's made from algae, plants, or even waste. But SAF is expensive, and it's rare. Today, it accounts for less than 0.2% of global fuel use. Most planes can't even run on it fully. Boom says its Overture will run 100% on SAF and still be 30% more efficient than Concorde. But if SAF costs $8 to $10 a gallon, which it often does, then just the fuel cost for a New York to London ticket could be around $2,000 per passenger. That's just fuel, not crew, maintenance, taxes, or profit. Boom claims its round-trip tickets will cost around $5,000. But even if that's true, over half of that would be going straight into the gas tank. And for companies like Venus, where the plane carries just 12 passengers, that's not a business model. It's a math problem. Concorde had an advantage these new jets don't: full government backing. It was a joint venture between the UK and France. Rolls-Royce, the engine maker, was nationalized. Airlines didn't even have to buy the planes, they were just handed over. Today's companies are startups, scrappy, innovative, but they're also alone. Boeing estimates that developing a brand new commercial airliner would now cost $50 billion. That's the kind of money these supersonic projects just don't have. One of the startups, Exosonic, had a relatively modest goal, Mach 1.8 using existing engines. They folded in 2024, just couldn't raise enough capital to survive. Ask the CEOs who will fly on these jets, and the answer is pretty consistent. High-value business travelers, executives, first-class flyers, people who already pay a premium for time. But here's the irony. Studies show that executives who commute long distances, the very ones who'd want supersonic, often perform worse than their local counterparts. Companies lose value, tenures are shorter, and if they live near a golf course, it gets even worse. So if the jet's loud, cramped, hot, expensive, and burns through fuel like there's no tomorrow, who's really signing up? Private jets already offer unmatched comfort. You can stretch out, take calls, nap. Saving a few hours might not be worth trading all that. These jets aren't just about speed, they're about experience, personalized service, flexible departure times, privacy from the moment you arrive at the terminal. For high net worth individuals, that comfort isn't optional, it's expected. Supersonic travel, on the other hand, comes with compromises: smaller cabins, less space, higher noise levels, even more turbulence at cruising altitudes. And unlike private jets, where itineraries shift on demand, supersonic jets would likely operate on fixed schedules due to cost and coordination. That kind of rigidity doesn't appeal to the ultra-wealthy. Add in security clearances, special training for crew, and more intensive maintenance, and suddenly the faster option looks like more of a hassle than a perk. There's also the branding problem. Private aviation markets itself as serene, luxurious, effortless. Supersonic still screams experimental. It's tech-forward, but not lifestyle-forward. And in a world where brand identity matters as much as performance, that's a tough sell, especially when passengers are choosing between a leather-wrapped jet cabin with chilled rosé and a high-altitude rocket ride in a space-age tube. There's no doubt, the dream of flying faster than sound still burns bright. The engineering is real, the prototypes are flying, the passion is there. But speed alone isn't enough. Noise, heat, cost, regulations, efficiency, comfort. Each one of those challenges has sunk a supersonic jet. And solving all of them? That's like trying to run a marathon while juggling torches in a wind tunnel. Could the next big breakthrough finally make it work? Maybe. But don't expect to book a Mach 5 ticket anytime soon. The future of supersonic travel isn't just about going fast, it's about going smart. If this deep dive into the world of supersonic jets got you thinking, hit that like button and subscribe to the channel. Share this with someone who always seems to be in a hurry. And if you're passionate about tech, speed, and storytelling, check out our Patreon to help us bring more of these videos to life. Thanks for watching, and as always, stay curious.